The course effectively deals with stochastic differential equations, their relation to PDEs. We should know in the middle of the course that they are needed for some practical reasons. And then we will talk during this course a bit about numerical approximations and how to model effectively solutions to stochastic differential equations. We will approach this in steps. So firstly, we will need to define what a stochastic differential equation is. For that, we will need to define what a stochastic integral is. So if you look at the ordinary differential equation, and you want to add some noise here to model some noisiness of the medium. For instance, you can consider a heavy particle. So this is like a dynamical equation for this heavy particle that moves in a random media that has some random interactions that push this particle around. You may start about thinking some additional term that affects this. So for that, it's easier actually to write it as this. So there is some force. This affects how large these pushes are, and this affects some random interactions. And to define this, we will need to go through some steps. Now, more precisely, we will need to define what this thing is and how it can be defined properly. This is called a stochastic integral because it is integrates with respect to some stochastic random process. There are different types of stochastic integrals, and there are different approaches to how to build them. So two main classes is when here we have ordinary Wiener process or Poissonian process. These are very different integrals, but can be mixed. They can be approached in a unified manner via theory of martingales. We are, however, going to approach it in a more old school way by hands for a number of reasons. One, because I think it's beneficial, and quite a few people agree with me that you need to construct stochastic integrals by hands at least once. And secondly, because we also want to talk about pathwise properties of such objects. But regardless of what we intended to do, we can keyboard a bit here. We will start with discussing Wiener process today. More precisely, we will talk about Markov properties and filtrations, because filtration is the object that is necessary to start the theory of stochastic integrals. So we have omega fp is our probability space on which our objects are going to be defined. So recall that omega is a set of elementary events, phi are elementary events, F Gaussic is a sigma algebra of events, random events, and P is a probability measure. Let's speak about one-dimensional Wiener process. Also, it is often called Brownian motion, and I will use this term interchangeably without any notion, without caring due this course. So a Wiener process, a Brownian motion one-dimensional, is a random process that is a collection of random variables defined on this omega fp, wt, t greater than 0. Sometimes you can discuss Wiener process on an interval from 0 to t capital, say. Nothing really changes. Such that, firstly, w of 0 equals 0. All trajectories start at 0. This collection, as a random process, has independent increments. That is, for any t0 less than tn, wt1 minus w0, which is just 0, wt2 minus wt1, wtn minus wtn minus 1 are independent random intervals. And 3 is Gaussian finite dimensional distributions. So it is sufficiently to say that distributions, the law of wt minus ws is a Gaussian random variable with 0 mean and variance t minus s. If you know distribution of such increments, we using independence can derive the distribution of any finite dimensional distribution. It is often added in the definitions that W has almost surely continuous trajectories. Recall that trajectory is trajectories. And what is trajectory? It's for every omega, we can define this function Wt omega continuous trajectories. Obviously, this is going to follow from previous properties by the Kolmogorov-Chantsov theorem automatically. And again, Wiener process can have different definitions. So, for instance, alternatively, we can say a Brownian motion in Wiener process W is a Gaussian process with 0 mean and covariance. It's minimum Ts. That is mathematical representation of Wt, so 0, and covariance these two Gaussian random variables is just minimum Ts, and I will occasionally use T minimum S, this notation to shorten this, writing this minimum Ts. Again, this is sufficient to define finite dimensional distribution. So let's still recall that finite dimensional distributions of W, that is the distribution of Tn, are defined, for instance, by their characteristic function for any lambda 1, lambda n, arbitrary, real valued equal numbers is just e minus 1/2 gamma lambda lambda, where lambda, alpha is a vector in Rn, and gamma is a function n times n of size n times n and gamma Eg is just Te minus Tg, and knowing this we can write the distribution. So I will still write it just to remind you quickly that in particular mathematical expectation O of EWT is just minus T alpha squared, and that means that we can calculate any expectation of any functional one-dimensional motion of a Wiener process by just integrating over the Gaussian density, the x dx. So this is a very quick reminder of what a Wiener process is. Now, a Brownian motion started at x is a Brownian motion plus x. So we just assume that the starting point is x. Nothing really changes. We will, however, have not zero mean, but the mean is going to be x. But otherwise, we can just take standard Brownian motion started at 0 and just shift it by x. I will rarely care about this form. And now a multi-dimensional Brownian motion is a vector of independent one-dimensional Brownian motions. So we just have W1, Wn in Rn. Sometimes people call all these objects standard Brownian motions, and one can define Brownian motion such that, say, mathematical acceptance squared at 1 is sigma squared. So the variance is not 1 at 1, but sigma. Obviously, nothing really changes. It's just some change of R. So we will always discuss standard Brownian motion with zero mean and having unit variance at 1. So I suppose that we are...
Can you hear me well?
Yes.
Can you please go up to the characteristic function? Don't we have to divide by 2 here in the exponent?
Oh, yes. Obviously. Thank you.
Yeah.
Yeah. Oh, it's not continuous. Continuous modification. I'm not going to talk today. Now, sometimes it's beneficial to get rid of this omega fp. So we don't know much about omega fp, so sometimes we can think as beneficial to have a very standard way to define a Brownian motion on one specific and well-known space to speak, for instance, about measurability of some functionals of Wiener process in a unified manner. So assume that W is a Brownian motion on some unknown space, because you can build Brownian motion by hands on some probability space. And we want to redefine it. Redefine W as a random process on another probability space, C, beta, and PW, where C is just space of continuous variables on 0t on 0 plus infinity. Beta is a Borel sigma Albert on C. And PV is a so-called Wiener measure we will explain in a moment how to obtain. Such constructions, when Brownian motion is given as a random process on this probability space, is called canonical model. So let's make a remark that by general we only know that W belongs to C with probability 1. We can construct or assume, we can construct Brownian motion in the way that not all his trajectories might be continuous, because the definition only has Brownian motion has continuous trajectories almost surely. Then without changing mass, we can define W. So this is W of omega is equal just W of omega is W is continuous. And say just equal a constant when trajectory is not continuous. So then obviously we have W equal all W is probability 1. W is a Brownian motion. And in particular, finite dimensional distribution are exactly the same. And we usually care about finite dimensional distribution, especially in the context of numerical methods. So one can say that for every t, probability W tilted equals the original W of t is just 1, is a version or modification. And two random processes that coincide for every t with probability 1 are called versions or modification of each other. Now, we will consider topology of uniform convergence on C. So again, a remark. If C 0 of t, this is not a convergence of uniform topology of uniform convergence, it's convergence of uniform convergence on compact sets. So the distance is then given rho f g is sum over n squared over n natural 2 minus 1, and here just say 1 minimum distance over 15 minus. C is a complete space with respect to this topology. So this is a very good set, a very good probability space. Talk about this. And now we can start defining our. So we start with omega phi. We will set I by I of omega is W of omega point. So this is now a function on C0t. This is very easy to see that effectively what we've done, we just, instead of considering Wiener process on omega phi, we passed by measurable function. We will see that this is a measurable here. So let's even.
Do we consider C0t or C0 infinity here?
It doesn't matter.
Okay.
It just doesn't matter. You can do everything with 0t or 0 infinity. You will just need, here on 0t you have just uniform convergence. Here you will need uniform convergence on compact sets. However, the topologies and the way Borel sigma algebra, as we see in the minute, are constructed is exactly the same. So nothing really changes.
Yeah,
So,
thank you.
So this mapping is a measurable mapping. For that, we need to recall what cylindrical sets are. So what are cylindrical sets? Given a selection of indexes on 0t, a selection of Borel sets on R, just for the sake of clarity, a Borel sigma field is a sigma field generated by open sets, or in case of R, closed at the same point, at the same time. And Tn of In Yn is those functions in our C that f at moment tk lives in ak for all k. So this is called a cylindrical set. And cylindrical sets generate Borel on C0t. We said that Borel is a Borel sigma algebra, so it's generated by open sets with respect to this distance. At the same time, cylindrical cells also generate See, this is effect from standard scores of probability of random processes. So if you know that you are good, if not, check in a textbook or just prove it. It's not hard to prove. You will need just to prove that open set can be approximated by these or using some other techniques. It doesn't matter. I will use this as a fact. And since these sets generate B, we only need to check that this holds or cylindrical. A, because it's a collection of sets generated sigma algebra, then checking measurability it might not happen for all sets in the sigma algebra. We just can take sets from the sets that generate the sigma algebra. But it's very easy to see, because what is this? It's I inverse function of this expression, but this is exactly those omega, this omega tk belongs to ak. K from 1 to n. So I will write it as pt minus a1 intersection p minus 1 t n a n, where this pt is a projection, so it acts on c0t and ends in r, and pt of omega is just omega at t. This can be defined for all t in 0. T capital. Now, every pt is a continuous function in the terms of uniform metric, because the difference of pt of omega 1 and pt omega 2 is obviously pt omega t is obviously less than maximum of s ranging from 0 to t capital omega s1 minus omega s2. So this is a continuous function, thus it's a measurable function. Now, this is measurable, everything is measurable, so we can conclude that this is a good measurable mapping I capital. Now we can define our Wiener measure as just a push forward of the original probability under the action of the set, of this mapping. And in particular, this means that if we have to ask about a finite dimensional distribution of a Brownian motion, this is just the measure with respect to this. This is a measure of the cylindrical set, effectively. W T. It might be one of the best way to describe this measure because obviously we can write it explicitly. It's a measure on some functional space. And again, cylindrical sets define the measure also uniquely. This is a separating class. I suppose, again, I will just assume that you know this. If not, just look it somewhere. Now we can start working towards what we are really interested in. So next section is Markov properties and heating times. So we start with defining what a filtration is, because it's a very important object, stochastic integration. A filtration on some probability space, in most cases, this is just our C Borel on C P of Wiener, is a collection F T. Now here I will just assume that T ranges from 0 to plus infinity of sigma algebras such that, well, they all live in the original sigma algebra, and ft is less than fs if t is less than s. So this is a collection. One can think about a flow of information. Every sigma algebra gives us some information about something, and we have an increasing flow of such pieces of information. Now, the natural filtration of Brownian motion W is Fw of t given by sigma algebra generated by all values of our Brownian motion up to time t. So all values, all linear combination of functions of such expressions, they all live here. And a random variable tau, which can take infinite values. So sometimes I will speak about numbers that can be equal to plus infinity. So obviously this annotation, one can define a correspondent version of the real space, but one can think that this is either a number or this is plus infinity, one specific point is called a stopping time with respect to some filtration. Some filtration, this is now not a natural filtration necessarily. This is just a filtration sum. And we will actually work with other filtration. If for any t greater than 0, such sets belong to Ft. Now, a remark, important. Sometimes in all the books, such things are called Markov times. And a stopping time is a Markov time that finite almost surely. But in most modern book, this is just stopping time. But you need to be careful when reading older books. They have two-step classification, and modern book often just go in one notion. So let us understand why we even care about this. So let's look at some examples. The first one. Assume that we have one-dimensional Brownian motion. Started at some zero, which is less than some WA. Then infinitum, those moments of time, the WF hits A is the stopping time with respect to the natural filtration. Natural filtration of W. Indeed, tau greater than T is exactly for any S less than T, WS doesn't hit A. But because it's a continuous function, we can say this, that for any S belonging 0T and rational WS less than A. And this is obviously FFT. We can add this T to make everything work. So effectively, this is the simplest example of what is called heating time. If A is a closed set in R, I will speak mostly about one-dimensional Brownian motions, but nothing really changes during this lecture if you consider multidimensional Brownian motions. Maybe sometimes instead of modulus, you will need to write norm, but that's the only difference. Or we can just work with, I think, multidimensional inner D, W as a d-dimensional Brownian motion. Let's define tau as the first moment Wt belongs to A. Now, with respect again to the natural filtration of W, this is a stopping time. This is the reason why we're speaking about stopping times. This is a characteristic property of many good debut times. So the times when Wiener process hits some set for the first time. Let's prove that this is heating time rigorously. So step one will be the following. Tau greater than T is obviously the same as tau less than T. And we claim that this can be written as infinitum over all rational in 0T such that this infinitum is 0 where rho of x is the distance to A. So this infinitum, this is set is equivalent, saying that tau is less than T is equivalent to saying that infinitum of rational living on 0 of T of distances from the value of Brownian motion to our set A is 0. Indeed, if this is true, if star, let's put here star, is true, then instead of the original event, we can consider this event and this event. can be written as
I think it's a union, yes, so we'll find such, not for all.
uh, infinum. We can read is the following form. Yeah, let's write it differently. Yeah, it's not right. I wrote something strange. Let's write it as this form. So if infinitum 0 is 0, that means that it less than any positive epsilon. On the other side, we can just now get rid of epsilon and say that this infinitum is less than 1 over n. Right? Right. Now, this infinitum is measurable. I believe because infinitum rho WR. Now, this is infinitum over the set. If infinitum is less than x, or say like even greater than x, maybe we will do it. Let's think which direction we should go. If infinitum greater than x, maybe it's not sufficient. If infinitum over some set is less than x set. Okay, let's start with this. So for infinitum to be greater than x, sorry.
I think we can just write the definition of the infimum using so the set like the set theory. So for each epsilon, we can find such R that some inequality holds.
Yeah, I'm trying to do this. I'm just not sure which direction should we go, this or this. If infinitum, if for all elements in some set we have the inequality less than x, that infinitum is also here, but I want the other direction. For this infinitum to be greater than x, this means, no, okay, we put it formal, do this. So to check that this is a FWT measurable random variable, it is sufficient to check that this belongs to FWT. Because it's a random variable, we can check measurability of events in a different way. So this means is if it's greater than x, that means that there exists again n greater than 1, that this infinitum is greater than x minus over n. But it's a union of such sets. Now this is a union over n greater than infinitum rho WR greater than x minus 1 n. And now if infinitum WR is greater than something, it requires all elements of the set that this infinitum is taken over is to be greater than this. Is it true? Yes, if all elements are greater than infinitum, and if infinitum greater, that means that all should be 0, but they can be equal to x minus 1. So we need this additional step to get rid of this. So if we have this star, we can conclude. Now we need to prove star. So step 2 is proving star. 2, star is true. Star is true, and let's prove it directly, I think. Let W, now we leave, we can take that W is effectively just our W, a trajectory, because we can switch to this canonical model of a Brownian motion is such that this infinitum is 0. Then what does this mean by definition? Exists some sequence of times such that they belong to this set. Oh, this is T small. And rho of WTN converge to 0. This is by definition of the infinitum. Now, from here it follows, because we live on 0 of T, and this is a compact set, then there exists a subsequence, and there exists S that belongs to 0T. It may not be rational, however. The T and K converge to S. But this means the W of S, now we will prove this also, is the limit when K goes to infinity, rho W T and K. This is 0. And this means the tau, the first moment this happens, is less than T. So what we need to know is that y rho is a continuous function. But it's easier to see. It's easy to see. Continuous function. Because if we take any two points in RD and z belonging to A, then x minus z is less than x minus 1 by the triangle quantity, and y minus z. Now, if you take infinitum in both sides, you can do this by yourself if you prefer to do it in terms of epsilons, but it's quite easy to understand why. Which is just that rho of x is less than rho of y plus the distance between rho and distance between x and y. And obviously we can change, switch from x and y to y and x, and analogously prove that rho of y is less than rho of x plus the distance between x and y, which immediately means that this is even actually ellipsis continuous function. So since it's ellipsis continuous function, we can conclude that this holds, and indeed, if this infinitum is true, then tau is less than T. Now, suppose that omega is such that tau less than T. If we assume, from contrary, I think this is easier. If we assume that there exists epsilon such that this infinitum is not 0 but greater than epsilon, then again, any sequence of such numbers, the Tn converges to tau. On one side, we have that this is a limit of this Tn, but this is greater than epsilon, but this should be 0. So we have a contradiction. It cannot happen. So a first hitting moment of a closed set is always a stopping time, hitting time for an open A. Now this is trickier because actually this is not true. Hitting time of an open set is not guaranteed to be a stopping time. And that's why we need a slightly more advanced filtration instead of a natural one. More precisely, we will define Wt plus or alternatively, we can write over f of epsilon intersection t plus epsilon for any t. This is a so-called a right continuous filtration in the following sense. If we take it and do the same procedure of augmentation, this procedure of making filtration bigger in some sense is often called augmentation of a filtration. If we take this augmented already filtration and apply the same procedure, we effectively see this because we now have 1 over epsilon and 1 over epsilon 1. We have this equality. So such filtration are called right continuous. They coincide. So if we take this notation, GT is GT plus. This is right continuity. We can peek a bit into the future and this doesn't change anything. This doesn't add new information for this filtration. Then proposition I am interested is as follows. Tau is a GT stopping time. And tau is not a natural filtration at stopping time with respect to the natural filtration, unfortunately. Let's start with the first fact. So thus tau less than t can be written as such intersection again the same trick that we switch to rational. This should be a moment of heating. And I will leave this as an exercise if you think this is not evident. Now we can, since this is intersection, we can work with this set directly. This is a union of a rational belonging to 0s. And this is obviously in FWS, because this is FWS measurable. This is actually FWR, and R is less than S measurable. So our tau less than T can be written because of this as an intersection S greater than AS, where every AS is FWS measurable. But this means that tau belong FWT plus by definition of the sigma algebra. So indeed, it's a hidden stop in time with respect to this augmented filtration, because we had here to move a bit forward in time. Now, the second step is a bit trickier. Now we know we have our canonical model. So let's consider any tau, any function continuous on, say, 0t, such that for s smaller than t, f of s doesn't belong to the closure of A. T is exactly on the boundary. So this is our open set. This is a trajectory that behaves like this, and it hits boundary exactly at time t. And let's introduce a set, say K, which is exactly those elementary events that agree with this trajectory on 0t. Now K belongs FWT. By the definition of what FWT is exactly the information that are available at IT and earlier. But K is effectively an elementary event. There is nothing smaller in T, because this is exactly, we know that in the canonical model, omegas are just functions, and we take the function. So this is an elementary event. It can be like divided in any sense. However, this is strictly smaller than 0t, which is our key. Why? Because to know if the first hitting time and open set is less than 1, is less than t, we need to know what happens after t, because it sits on the boundary. It can go inside of A, it can go outside of A, in the sense that it hits boundary and then he go here, or can go here. So this is a non-trivial subset of the original K, but K cannot be divided. This means it cannot lie in this FWT. One can try to argue, but we know that Wiener process behaves in a very strange manner. It starts anew at every moment of time, and maybe if we hit boundary, we know that if it hits some one-dimensional Wiener process, if it hits some level A, it immediately goes up and below. It behaves like this. So maybe it's not even possible, and the possibility of all such events in any sense is just zero. So maybe if you ignore bad events of probability zero, so-called null events, we can deal and make this work as a heating time. And this is actually true, but to work in this direction, we need some additional constructions. Alternatively, also, one can say, okay, but maybe we can, instead of adding this null events, also consider this right continuous filtration. So we need to understand what we need to do with the filtration of the Brownian motion to make sure that at least heating times of open sets are stopping times. So we start with the first idea. And we will see in the end they all agree in the sense that they all produce the same end results. So null sets and Gothic is those subsets of the original probability space. There exist two measurable sets that encapsulate our set A and P of A. 1 is equal to P of A2. So effectively, this is a set that can be approximated by real measurable sets, and those approximations have the same measure. And now we can define the completion of the original filtration, natural filtration. T is a sigma algebra when we add here our null sets. Now, a small remark. Effectively, original probability space is usually already complete in the sense that F contains null sets. It's not necessarily true, but in most cases it's tacitly assumed, because otherwise you can have a bad situation. For instance, you can consider just omega equal to 0, 1, F to the set of Borel sets on 0, 1. P is just uniform distribution. And if A is not a Borel sigma set, we can have like define such random variables with the just constants, define psi equal to indicator of A, and then we will have that psi1 converge to psi almost surely, because for almost all omega, this holds, but psi is not even a random variable. It's indicator of a non-measurable set. And that's why in the definition of convergence almost surely usually say that you have a sequence of random variables, you have a random variable, and this holds with probability 1. But even to stop thinking about this, people usually add just null sets into this construction from the start. So it seems that doing this with our filtration, we shouldn't lose much generosity. And indeed, this is not going to happen. Now, another remark, very important. Usual conditions. So often in literature, you will say that we consider a filtration that satisfies usual conditions. A usual condition is inclusion of null sets and try continuity. So it's very natural to see to include this, and inclusion of null sets is useful because we just talked about this. And right continuity is, we're getting participants, by the way, somewhere. We got them. And right continuity is useful for a number of reasons. First of all, heating times are well behaved. Secondly, it's easier to work with martingales with respect to this filtration, but if you're not going to go into details. And effectively, every augmented with null sets filtration, natural filtration of a good, strong Markov process, in particular Brownian motion, is already right continuous. So effectively, we don't lose anything by imposing such conditions, at least for strong Markov Feller processes. And to discuss it a bit in details, let's return to discussions on properties of Brownian motion. The first is just Markov property. Not strong, but just ordinary Markov property. I will use the following version of this theorem. So consider a Brownian motion. And then with all s greater than 0, the process. I'm sorry, I can't see chat. There is a way you can be sure what does. I have some chat. Okay, I'm sorry I missed it. I will try to next time to react to it properly. Is a Brownian motion independent of the original filtration taken at S? And to answer this, yeah, I think we progressed to countable at that point. So effectively, if we stop Wiener process, minus WT, minus WS. Let me write it properly. Stop Wiener process is fixed time S. We again get a Wiener process. You should know that it is very easy to check just using Gaussian properties of the Wiener process, because everything that happens after is a Gaussian variable independent of the value of WS and everything that happens before. So I assume we know that. We will progress to the second theorem that, for instance, says the following. W plus, so the right continuous augmentation of the natural filtration of the Brownian motion and the filtration augmented with null sets, with with null sets as such that this is still true. The same process. I will denote WS is a BAM Brownian motion independent of FWS plus and FWS. Now, to prove this result, we need to recall some stuff from the course of probability. And what is most important, I will need to recall P lambda theorem. So a system of sets A is called a P system if this holds it's closed under intersections. That's A Gossip. Use A Gossip is also an A Gossip. And a system of sets A is called a lambda system if the following three conditions holds. Firstly, the whole set should be in A. Proper differences stay in A. If A1 is larger than A2, we can take this proper difference, it's still A stays in A. And if we have in such increasing limits, if we have a sequence of sets from A, and they are increasing, then their union, which is effectively like the limit, stays in A. Then the theorem we will use a few times. What follows is called a P lambda theorem. And it says, if a system of I sets contains another system of sets, let's C, and C is a P system, and A is a lambda system, then the smallest sigma algebra generated by C is included in A. Already. It's sometimes formulated in the courses of probability theory as the theorem, in the form of the theorem that states pretty much the same, but in terms of so-called monotone classes. I still think that this is more beneficial for us and honestly in general. I assume that we know this theorem. If no, please check it in the corresponding course or in any textbook, advanced textbook on probability theory, or just prove it by yourself. It's not extremely hard. Now we can return to proving the statement we had here, that all these are preserved, that independence is preserved if we consider slightly bigger filtrations. So step one, now consider set A that belongs to plus and some bounded function, independent bounded function on R. So since by definition, this holds, by definition of the right continuous augmentation, A belongs T plus epsilon for all epsilon greater than 0. This means that for any S, now we fix our S, such mathematical expectation can be decomposed in the following sense. Let's add one layer of conditional expectation. Now, this part is obviously independent of this by the Markov properties that we just formulated, ordinary Markov property. And this belongs to this. So effectively, we can decompose this into two product of two sets of two vectors. This is because of the Markov property. Now, like a remark or recollection. So to prove the two sigma algebras are independent, on such devices. Why? So we are effectively proving the sigma algebra generated by Wiener process up to the time t, and what happens is the sigma algebra generated of all shifts of what happens else are independent. So this is our two sigma algebras. And the proposition I'm here referring to subsumes that are sigma algebras. And B is a P system. A classical example of a P system is closed set. Its intersection closed set stays closed. And assume all from A and B from B, PA intersect B is just PA, PB. So we I change notation on the fly and don't like it. AB systems of sets. B Gaussic is the sigma algebra generated on B, and B is a P system, and A is already a sigma algebra. Then if for any sets for our sigma algebra and any B from our B capital, so not all sets from B Gaussic, but just a part of them, we have independence of the corresponding events. Then A and sigma of B are independent. Let's actually prove it to show some technique. Yeah. So let's define C as those sets. So for all A belonging to A, PCA can be decomposed in this. So effectively, this is a set of all sets that are independent of the sigma algebra A capital. Then obviously, C contains B by assumption. We said that this is true for all sets from our original system of sets, from our P system. And C is a lambda system. Why? Obviously, omega belongs to C, because P omega A is just P of A. of P of omega, because P of omega is 1. Now, if C1, C2 belong to C capital, and C2 is greater than C1, then P of C2 minus C1 intersection with A is PA. Again, by our assumption, but the construction of C capital. And last, if we have a sequence that lives in our C capital and it's increasing, then P of union of Cn intersect with A for any A belonging to our regional sigma algebra A. This is effectively mathematical expectation n greater than 1 indicator of A. Because everything is bounding, we can use the Lebesgue theorem. Which is exactly PCN limit P of A, which is exactly PC, PA, because again, of the properties of the probabilities matter. So this is indeed a lambda system that contains the original P system, and it's therefore it contains also the whole sigma algebra generated by E capital, which is exactly the definition of the dependence of two sigma algebras. Now, one question is that in our case, we have two sigma algebras. The first one is FWS plus and sigma algebra generated by T plus S minus T for all T. These are our two sigma algebras that we have. But the device that we considered is actually of this form. We have here some continuous function. This is not the indicator, but say any closed set can be approximated by continuous function. So if A is a closed set, we can set f, say epsilon of x is f, should be 1 minus, I think, rho of x, where rho is a distance to x, to A. We already considered such expressions, and f of x is just such function. It's 0 when it gets too large, and it's just y minus n when x lives here. I will leave this an exercise. So this is sigma algebra generated by such random variables. We can consider this is a sigma algebra generated by images of closed set under actions of such random measurable mappings. And we can, by this approximation theorem, instead of closed set, consider just good functions. So effectively, we proceed as follows. We have returning to where we started. Oh, it crashed. Lovely. We started from A returning to the beginning. We have A that belonged to F T plus, and we established that mathematical expectation indicator of A F W plus epsilon plus epsilon is equals P of A F W T plus epsilon S minus W T plus epsilon S here S plus epsilon. Now we can go to the limit in the right and the left hand side by the Lebesgue convergence theorem to obtain the following. And here we get P so this is also equal. And now we can take any set of the form, let's say B, where B is a Borel sigma set, and B is closed. And because we have this, we can now approximate indicators of such with function f. We can then go to the limit in the left hand side and the right hand side again to conclude that PA, PB equals PA intersection B, where A belongs to F plus S, FW plus A, and B is of this form. And this proves the independence of the corresponding sigma algebras. Now we can quickly finish the second step. I will actually maybe even prove a slightly. Let's even consider this. So we took Pasley null sets, then right continuous version appears. So we did two augmentation with null sets, and by taking right continuous version, by taking right limits. Then if we consider F any set from here, this effectively means that which means that for every epsilon, there is this set that is measurable with respect to this WT plus epsilon without null sets. The symmetric difference of our original set and our A is null, because they can be like slightly moved by null sets and still exactly what we have. And now we can consider exactly the stuff as is previous. Step. Again, we can do the same strong Markov property, and we will arrive at PA epsilon mathematical expectation T plus S plus epsilon minus T minus W S plus epsilon. And again, we can go to the limit when epsilon goes to infinity, because actually this is already P of A because of this property. And we again can conclude these two sigma algebras are independent. So effectively augmenting the natural filtration of the Brownian motion preserves Markov property. And next time we will finish this topic by proving that the strong Markov property is related to the fact that augmented with null sets, the natural filtration of the Brownian motion is automatically continuous. And this is exactly the filtration that we will use later to define a stochastic integral properly. And luckily, I think this is going to be the last lecture with so much on measurable issues. Do you have any questions?
Not yet.
Good. That's all for today, and
Could you please go to
we will
the
see each other, I
definition of
hope,
the
next Wednesday at the same time. Goodbye, everyone.